Assalamu alaikum wa rahmatullah. Welcome back. And we are continuing our lectures on the network layer. So, the last issue that we have discussed was the IP protocol, the Internet protocol. We looked at the details of the IP packet header. So, we learned all the extra information written inside the IP packet header. Now, in continuing our discussion, we would like to look at other protocols that work at the network layer. Of course, we understand the Internet Protocol IP is the most important one. So it is the main protocol working at the IP layer. This is the one that allows different machines to communicate with each other. But in addition to the IP protocol, in addition to the Internet Protocol, we have some other protocols that help. And one of them is called the Internet Control Message Protocol, ICMP, the Internet Control Message Protocol. It's nothing new. However, we would like to look at it in one place. So to look at all these issues in one place. What I mean here is the following. In our previous discussions, we came across special messages that need to be sent sometimes, like hello message. If a router wants to understand who the neighbors are, like echo, if a router would like to know how far away neighbors are, what is the delay between me and my neighbor, and so on. So we came across some special messages. I would like to tell you now that all these special messages are governed, are organized by one protocol, which is called the Internet Control Message Protocol. So what is ICMP? What is the Internet Control Message Protocol? It is that protocol that organizes the sending of the special messages. Special messages like what? We have seen many of them, but it's a good chance to have a look at some of them here in one place. So one of the special messages is called destination unreachable. Imagine that a router in the middle of the network receives a packet. Of course, the router's job is to check the destination address. So look in the packet header, find the destination address, and then consult its own routing table to decide which way it will send this packet. So what's the direction of forwarding? What is the next hop? Now, if it cannot find this destination in its routing tables, it means that I cannot send this packet because the destination is unreachable. I don't know about this destination. So what is the router's option in this case? It would have to discard the packet and also send a special warning message back to the sender that I was not able to send your packet. So this is destination unreachable. Another special message is time exceeded. Imagine I'm a router inside the network and I receive a packet that I need to forward. However, I noticed that the time to live field in the packet header is 0 already. So which means that I'm not allowed to forward the packet. I have to discard it. I have to drop it. However, I do that, but I send a warning message back to the sender, which is called time exceeded. So time exceeded is another special message, which is part of the ICMP protocol, the Internet Control Message Protocol. Parameter problem. Imagine I'm a router inside the network. I receive a packet, but I find that some part of the header has an invalid value, so invalid parameters in the header. There is a mistake in the packet. I need to drop it and send a warning message back to the sender called parameter problem. Source quench is the choke packet that we talked about last time already. So it's a way to avoid congestion. It's a congestion control mechanism, and if that mechanism is used, we have a choke packet, and the choke packet is actually, again, it's another special message which is part of the ICMP protocol. We have seen echo and echo reply. If I would like to calculate the delay between me and my neighbor, so I send an echo packet, I receive an echo reply, and then using a timer, I have an estimate of the delay between me and you, between the router and its neighbor, and it's used in distance vector routing, it's used in link state routing. So in routing protocols, routers all the time would like to know the delays of their neighboring links. So these are also echo and echo reply are also part of the ICMP, the Internet Control Message Protocol. You can have a look at all that. It's very clearly mentioned and it's very clearly explained. We talked about most of it. So as you notice, this is really a datasheet kind of information, but we understand ICMP by now. Now, The next helping protocol. So again, let me put you back in context. The IP protocol, the internet protocol, is the most important protocol working at the network layer. However, we have some helpers, we have some helping protocols. ICMP was one of them, the one that we have just finished, the one responsible for sending all the special messages, all the warnings, and so on. In addition to that, we have another very important protocol that helps IP. It's called ARP, the Address Resolution Protocol. So to explain why we need it, let me use this illustration. So let's recall together that we have a packet and the packet gets encapsulated in a frame. So we understand that since the introduction. You know, the packet belongs to layer 3. The packet belongs to the network layer. So if we imagine a sending machine, and at the sending machine at layer 3, a packet has been produced, the packet has been generated. In the packet payload, we have part of the message that need to be sent. However, we have a packet header as well that contains a lot of extra information. We have seen that in full detail, but what we need to focus on now is that in the IP header, in the packet internet protocol, the IP header, we have the source IP address and we have the destination IP address. So the IP address of the sending machine and the IP address of the final destination machine, that's written in the IP header. Now, the packet belongs to layer 3, to the network layer. Is that layer responsible for the actual physical transmission? No. So for the network layer to get this packet sent, it will give this packet to the layer below, the data link layer. Now, the data link layer will add another header that we call the frame header or the data link layer header in short. And of course, the actual format of this header will depend on which data link layer protocol is used, which depends on the network technology. So whether this is an Ethernet header or Wi-Fi header, or it depends on which network is used. Now, imagine that this is an Ethernet, so we are connected to our campus network. So this would be an Ethernet header. We have seen in a previous chapter, we have seen the details of the Ethernet header, but what we really need today is the source MAC address and the destination MAC address. So the MAC address of the source and the MAC address of the destination are written in this header. And now the whole thing, so that green structure here is called the frame. So this larger unit is called the frame. And as we mentioned many times, you can think of the frame as the envelope that contains the packet. Now, to send this frame, it is very important that we have to include the MAC address of the source and the MAC address of the destination. Now, this is where ARP, the Address Resolution Protocol, kicks in. Now, the problem with the MAC address is that it's a physical address. It's a globally unique address. Every network card, whether it's an Ethernet card or a Wi-Fi card, any network interface at the manufacturing time, it gets a globally unique address. Usually for Ethernet, it's a 48-bit address, which is globally unique. So you will not find two cards that have the same address. So this physical address, it never changes. Unlike the IP address, which is more logical, it changes from network to network. I think you should remember when we talked about the IP addresses that the IP address is not flat. It's divided into two parts, the network ID and the host ID. So the IP address contains information about the network we are connected to. So if you get disconnected and you get connected to another network, so you move from campus to home, for instance, you check your IP address, it's not the same, it's different. However, the MAC address, it's physical, it never changes. And as you notice, to get this frame sent, to get this frame transmitted successfully, we need both source and destination IP addresses. These are written in the packet header. And we need also source and destination MAC addresses, which are written in the frame header. We need them both. Now, the problem with the MAC address is that the sending machine may not memorize all MAC addresses. Imagine I'm sending you an email. So I'm sending an email to someone at mit.edu. So a specific email address, which implies that the server is mit.edu. This is the university server. Now, What about the MAC address of the actual machine? I don't know that because it's physical. I don't have the databases that contain all these MAC addresses. However, getting the IP address is easier. So getting the destination, of course, the source IP address is just my own IP address. It's written in the packet header before I send the packet. But the destination IP address, it comes from the name of the server. So it comes from the name mit.edu if I'm sending this email, or if I'm browsing a website, cnn.com, the IP address of that machine will come from the name cnn.com. The internet has special servers called DNS servers, domain name system servers, that are responsible for translating network names such as cnn.com or mit.edu or sharjah.ac.ae. These names are translated by these servers into their corresponding IP addresses, or the IP address that has 4 decimal digits or 32 bits in IP version 4. So imagine I would like to send you an email. Before I send you the email, I will send a request to a DNS server asking what is the IP address that corresponds to mit.edu. I will get the reply with the IP address, so I put that IP address in the destination field here, so the packet is ready. So that consulting of DNS, domain name system, this is the easy part. Now, what about the MAC address? How would I get that? And this is the job of ARP, the Address Resolution Protocol. The best way to explain it is through a nice example here. It's a practical example, so you can think of this as a campus network. This is the main router of the network that interconnects the computer science LAN with the electrical engineering LAN. So each one of these LANs has a switch. So this is an Ethernet switch, which is connecting host 1 and host 2, and we could have some other computers connected as well. And now we have the electrical engineering network, which also has a switch. This is an Ethernet switch connected to host 3 and host 4. Now, let's have a closer look. Of course, these two networks, so these two switches are interconnected by a router. Let's have a closer look here at these numbers and all these details before we can go on. So each one of the computers here has an IP address. So this is host 1 connected to the computer science network. It has an IP address 192.32.65.7. Let's look at the IP address of host 2, 192.32.65.5. I think you are experts in IP addresses now. If we convert 192 into binary, you will notice it starts with 110, which means class C. So we're having, this is a class C network. This part of the internet is a class C network. It begins with 192. Now, what does class C imply? Class C means the following. The IP address, which is 32 bits long, it starts with 110. So these are 3 bits, which are always fixed. And then the next 21 bits represent the network ID, and only the last 8 bits represent the host. So we have 21 bits network ID and 3 fixed bits, so 24 bits in total are fixed. The only part that would change from machine to machine is the last 8 bits, and we can even see it from here. Look at these numbers, 192.32.65. These are 24 bits. 192.32.65, 24 bits. They're exactly the same, which basically gives rise to the idea that these two machines are on the same network, are on the same class C network. They have the same network ID. The first 24 bits are fixed, but the last 8 bits, so this 7 is different from the 5, which means this machine is different from that. Now, look at the switch itself. This interface leading to the other side of the network has also an IP address, of course. However, what we would like to focus on here is this address here, 192.32.65.0. This IP address, 192.32.65.0, we can think of it as the IP address of the whole network. We should be familiar with this idea. If instead of the host ID, so instead of the 7 or the 5, we just have 0, it means that we're talking about the whole subnet. We're talking about the whole network. /24 is just another notation for saying that the first 24 bits are fixed, which is another word for class C, but that belongs to the classless addressing, because /24, basically we can use / anything, but we did not talk about that yet. So for now, we can think of /24 as equivalent to class C. Class C means we have 3 fixed bits, 110, followed by 21 network ID bits. So in total, we have 24 bits that are the same for the network. And this is precisely what this /24, this is what this says. /24 means that we have 24 fixed bits, 192.32.65. This is the address representing the network. And this is evident by looking at the individual IP addresses, 192.32.65. It's the same. 192.32.65. It's also the same. But now, because these are actual hosts, their corresponding IP addresses have a host ID. So this is .7 and this is .5. Now, let's go to the other LAN, to the other Ethernet here. So I have a switch that connects host 3 to host 4. This is what we show. However, we could have some other hosts as well. Host 3 has an IP address, 192.32.63.3. So let's look at the 24 bits. So because this is also class C, let's look at these 24 bits. It's different from these ones. And this makes it evident that this network is not the same as that. Since host 3 and host 4 are on the same network, they have the same network ID. So if we compare the IP address 192.32.63, 192.32.63, it's the same. But the host ID, the last 8 bits, .3 and .8, these are different because we would like to distinguish host 3 from host 4. Also, this network address here, since we have .0, it means that we're not talking about a particular host. However, we would like to represent the IP address of the whole network, which is 192.32.63.0. Okay, what about the router here? The router. Now we have to be careful. This is a host. Host number 1, it's like my computer or your computer. It has one connection to the internet. It has an IP address. The router has 2 interfaces connecting this network to that network. Each interface has an IP address. This is something important here. The IP address is not a number for the machine. It's a number really that distinguishes a network interface. So that interface here, the left interface, has an IP address 192.32.65.1. And the interface to the right has an IP address 192.32.63.1. Notice something important. This address for the left interface is suitable for this network, 192.32.65, just like these machines. And on the right interface has an IP address 192.32.63.1. So .63 is suitable for this network, which makes sure that this interface is part of the right network and this interface is suitable for the network on the left. Now, what about the MAC addresses? Each one of the machines that we talked about has a MAC address as well. And in Ethernet, the MAC address is 48 bits. To keep things simple, let's think of the E1 as the MAC address for host 1. Of course, in real life, this is a number, a 48-bit number. Let's just call it E1 here. E2 is the MAC address for host 2. E5 and E6 are the MAC addresses for host 3 and host 4, respectively. The router has 2 MAC addresses. Each interface has a MAC address E3 on the left and E4 on the right. Now, what do we would like to talk about? So in the previous discussion, I just talked about the network that we have with all its details. Now we would like to do something. So I focus on 2 transmissions here. We have one example. Host 1 is sending to host 2 on the same network. Host 1 would like to send an email to host 2. What happens exactly? What happens is that host 1 will create a packet at layer 3 of host 1. At the network layer of host 1, it will create a packet, and that packet has a header just like this header. Of course, the IP packet header contains the source IP address and the destination IP address. So what are the IP addresses in this packet? The IP address, the sender, the source IP address is this one. So IP1, 192.32.65.7. This is the source IP address. The destination IP address is 192.32.65.5, which is called IP2 to keep things simple. So that packet here has a source address, IP1, and a destination address, IP2. Now, what happens with this packet? Of course, the source, by looking at the destination address and by comparing the network ID, it knows that the destination is on the same network as mine. So imagine I'm host 1, you are host 2. I just created a packet that needs to go to you. By looking at the destination address, which is 192.32.65.5, comparing with my own, I know that you are on the same network as mine. Since you're connected to the same network as mine, I know immediately I can send you this packet immediately. It goes to you directly. It does not have to go to the router. So what goes to the router? Things that have to go outside the network. So if I need to send to host 3 or host 4, then I have to visit the router first, as will become evident or clear in the next example in this transmission. Now, host 1 is sending to host 2 by looking at the IP addresses, the source IP, which is IP1, the destination IP, which is IP2, the sending host. Host 1 knows immediately that the destination is on its own network, so it will send to it directly. How would it do that? By giving this packet to layer 2, to the data link layer. Now the data link layer will add a frame header which contains the source MAC address and the destination MAC address. The question is, which are these MAC addresses? Who is the sender? Host 1. What is its MAC address? E1, so that goes in the frame header. E1 goes in the frame header. Who is the destination? E2. E2 is the destination. Why is it the destination regarding the data link layer? Because I will be sending the packet directly, and we will notice the difference when I talk about another example. Host 1 sending to host 4. We will see another example a little bit later. But for now, host 1 is sending to host 2. We mentioned several times, this is a direct transmission from host 1, of course, going through the switch. However, we mean it does not go through the router. So the destination MAC address is E2. So this is how the frame looks like. This is how the frame, how it looks like. Of course, the frame has a frame header containing the source and destination MAC addresses. And inside the frame, we have the IP packet header, which contains the source IP and the destination IP addresses. Okay, so this is exactly how the frame looks like. Or focusing on the headers, focusing on the important part of the headers. So we have the source data link layer address, the source Ethernet address E1, and the destination Ethernet address or MAC address E2. And then inside the packet, we have the source IP address IP1 and the destination IP address IP2. Now, what happens with this frame? It will go to the switch. Now, how does the switch work? We talked about switches or bridges in a previous chapter. The switch uses the MAC address. It does not work with the IP address. It just checks the MAC address. So it will check the MAC address of the destination, which is E2, and then it will forward to E2 depending on its own forwarding table. So that frame arrives. Of course, host 2 will understand it is intended for host 2. It will accept it. It will see, yes, this is my own MAC address. So the data link layer, layer 2 of host 2, will act upon the frame header. It will check the destination MAC address. Yes, it's me. It will accept it. Whatever I need to do with this header, there is a trailer usually as well with error control information. So I will check errors. Maybe I correct them. And then this header is removed. And of course, what remains is the packet, which will go to layer 3. So I'm still here at host number 2. The packet will go to layer 3. It will check the destination IP address IP2. Yes, that's me. Whatever processing needs to be done at the end of the day, host number 2 here, host number 2 will have the actual message that we wanted to deliver. Now, what I mentioned so far is an explanation how the packet travels, how does it arrive at host 2, which is something on the practical side. However, our title was ARP, even in this slide. Our title was ARP, the Address Resolution Protocol. We did not really talk about that, and let me go back to this context. For that example that we have just finished, host 1 is sending a packet to host 2, so that packet will be encapsulated in a frame, and in the frame header, I always refer to this picture. In the frame header, we need to include the source MAC address, which is mine. I know my own MAC address. However, I need to include the destination MAC address as well. So the source MAC address E1 is known. I'm talking about host 1. Imagine it's me. I know my own MAC address, so I put it in the frame header. What about the destination MAC address E2? How do I know that? Now, that's sometimes hard for me to know because I don't memorize. Machines don't memorize all MAC addresses. So now host number one applies ARP. It applies the address resolution protocol to translate the destination IP address. This is easy to know. This is, as I mentioned in the first slide, knowing the IP address is easy, and this can be obtained through DNS, domain name system servers. So as host one, I know the destination IP address 192.168.65.5. I would like to obtain the corresponding MAC address. How do I do that? By applying ARP, the address resolution protocol. How does this work exactly? I send a broadcast message. I'm host one. On my own network, on my local network, I send a broadcast message which is asking who owns this IP address. Who is the machine that owns the IP address 192.132.65.5? So my ARP request contains an IP address that I'm asking about. Obviously, according to this configuration, according to this connection, that ARP request will go to the switch. The switch will understand that this is an ARP request. It will just forward to everyone, to everybody connected to the switch. So it will be forwarded to host 2 according to this picture. But if we have other machines as well, it will be forwarded to them, including the router, by the way, including the router from interface E3. Now, who will receive this ARP request? Everybody connected to this switch. Who will reply? Only host number 2, because it is the host that owns the IP address which was mentioned in the ARP request. So the ARP reply will contain this IP address and also the corresponding MAC address, which is E2. Each machine, as part of its configuration, it knows its MAC address. So this will go back to the switch, and the switch will forward the reply to host 1. So when the reply comes back, host 1 knows the mapping between the IP address 192.132.65.5 that we called IP2 and its corresponding MAC address E2. So this MAC address E2 will be extracted from the ARP reply, and then it will be put in the frame header itself, inside here in the frame that I wanted to send, which is the destination MAC address E2. So it goes in here, and now we have a frame that can be transmitted. As I explained already, it goes to the switch. The switch, by looking at the destination MAC address, it will decide to forward to host number 2. Host 2 has its frame. Now, so let me recap. We understand now how frames are transmitted and why we need the MAC address, because the switches will use the MAC addresses to deliver inside the local network. Now, what was the role of ARP? The role of the address resolution protocol was to obtain the destination MAC address, because I don't memorize it as host 1. As host 1, I don't memorize all MAC addresses. If I need to send a frame, I want to get the MAC address that corresponds to a known IP address, and I do that by applying ARP, which is simply sending a broadcast request that will go to everyone connected to the network, and the reply will come only from the machine that owns the IP address. And in the reply, we will have the mapping IP address and MAC address. This is precisely what we call ARP, and you have the explanation on the slide. So let me use the same figure here to explain the next example, which is, imagine host 1 would like to send a frame or a packet actually to host 4. Now, how does this packet look like? When we think of the packet, again, it has a packet header containing the source IP address and the destination IP address. So that packet header will be created at the sender host 1. Who is the IP address? What is the IP address of the source? IP1. 192.132.65.7. So this is IP1 here, 192.132.65.7. Who is the destination? What is the destination IP address? It's IP4, 192.132.63.8, and this goes in here. So we have IP1 and IP4, source IP and destination IP. This is in this header, in the IP header. So the IP address of the source, the IP address of the destination. Now, the sender, who is host 1, by looking at the IP address of the destination, 192.192.63 here. So the network ID is different from my own. So I know that this destination is outside my network. I don't know in which network it is. I don't care. I just know it's outside my network, which means I have to send this packet to the main router that I'm connected to the default gateway that I'm connected to the default router. So host number one would know it needs to send this packet to the router. Again, let's go back to the packet itself. The packet header has the source IP address, which is IP1, this IP1, and the destination IP address, which is IP4. This is IP4. And before transmission, that packet will have to be given to the data link layer of host 1, which will add its own header, the frame header, which contains the source MAC address and the destination MAC address. Now we understand very well from before that the data link layer, the scope of the data link layer is only one hop. So it is responsible for the transmission from host 1 to the router, because we know already that packet needs to go to the router. So if we look at the frame header here, the frame header, it has to contain the MAC address of the sending machine, E1, and the MAC address of the receiving machine, which is E3, not E6 yet. It is only E3. So that's the first frame that needs to be transmitted. Again, let me recap and let me mention again the first example. So we have host 1 sending to host 2. So we have a packet that needs to go from host 1 to host 2. To send this packet, how many frames were needed? How many envelopes like this were needed? Only one. Only one. So we have, this is the only frame that was needed, which contains E1 as the MAC address and E2 as the destination MAC address. E1 as the source MAC address, E2 as the destination MAC address. Let's remember this and remind you of the second example here. So these two rows here represent the second example. Host 1 is sending to host 4. By looking at the IP addresses, we know the sender is IP1. Again, this is IP1. And the destination is the IP4. This is IP4. By comparing the IP addresses, we know the destination is outside my network. As host 1, the destination is outside my network. I need to send to the router. Now, how does this happen? By sending, this is the first frame that corresponds to this transmission. So that frame will take the packet, from host 1 to the router. So who's the sending MAC address? E1. What's the destination MAC address? E3. Now, where does this frame arrive? It arrives at the router from interface E3, from the left interface that has MAC address E3. What will the router do with this? The router, again, it works with the IP address. So when it receives this frame, first of all, at layer 2, when it receives the frame, layer 2 will check the destination MAC address E3. Yes, it's me, so this frame is intended to me. And then, after all processing, this frame header will be removed, so we capture the actual packet. So layer 3 of the router, the network layer of the router, will have the packet. Now layer 3 will look at the IP address of the destination, which is IP4. Using its routing tables, it will decide to forward through this interface. So it will decide to forward through this interface. Now, before forwarding, of course, the packet which contains IP1 as the source IP and IP4 as the destination IP needs to be encapsulated in a frame again. So when the packet, think of this router. When the packet arrived at the router, it had a frame header. Now the router received this packet, the frame header was processed and then removed so that it can check the packet, decide which way it needs to send the packet by looking at the destination IP address inside the packet header. Now the router will turn into a sender. It was a receiver, now it will turn into a sender. And before sending, it will have to add another frame header, and that new frame header will contain the source MAC address and the destination MAC address. Who is the sender now? It's the router. So what's the source MAC address? It's E4. E4, because the frame will be transmitted through this interface. So the frame came through E3 and it will be transmitted through E4. So the source MAC address here with the second transmission of this example, the source MAC address is E4. What is the destination MAC address? Now it's E6, because the second frame will go from the router to host number 4. Now, to summarize all this, in the first example, we had a packet going from host 1 to host 2, because both hosts are on the same network, that packet transmission goes through only one frame. So it is implemented by sending only one frame from host 1 to host 2 directly through the switch. Now in the second example, we have host 1 that wants to send the packet to host 4. Since host 4 is on another network, this transmission will happen through two frames. Two frames will be transmitted as part of this transmission. The first frame goes from host 1 to the router. The first frame goes from host 1 to the router. That's why E1 is the source MAC, E3 is the destination MAC. And the second frame goes from the router to host 4. That's why E4 is the source MAC and E6 is the destination MAC. Now, in these two transmissions, in the transmission from host 1 to the router and in the transmission from the router to the actual destination host, for these two transmissions, if the destination MAC address, E3 in the first one and E6 in the second one, if the destination MAC address is not known to the sender applies ARP. So again, in the first transmission, if the sender does not know the router's MAC address, E3, however, it should know it because this is a router, so it's well known, but if it does not know it, it can obtain E3 by applying ARP, sending a broadcast request to everyone connected here. So that broadcast request will go to host 2 and to the router. The router will reply with its own MAC address. And in the second transmission, if the router does not know the MAC address of the final destination, usually it would not know. Before sending that second frame here, it will apply ARP to obtain this E6. So it will send an ARP request who owns the IP address 192.32.63.8. So that request will go to host 3 and host 4, everyone connected to this LAN, and only host 4 will reply with the mapping, its own IP address and the MAC address. So that's basically two practical examples. How is a packet transmitted from host 1 to host 2? And how is a packet transmitted from host 1 to host 4? And also along the way, we learned how ARP, what is the role ARP plays? So to summarize things, the address resolution protocol, ARP, the role of ARP is to translate a known IP address into its corresponding unknown MAC address. So I use ARP to obtain the MAC address that I don't know. And we have explained it in full detail. So let me skip this explanation and go to that slide. How can we still optimize things? What did we notice about ARP? So in ARP, we have a sending machine that does not know the MAC address of the receiving machine, so it sends a broadcast request. Who owns this IP address? Who replies? Who sends an ARP reply? It is that particular machine that has the IP address mentioned in the request. Now, what can the sending machine do? So let me go back to the context. Imagine host 1 wanted to know about the MAC address of host 2. So it sent a broadcast request. Eventually, the reply will come with this IP address, 192.32.65.5, and the MAC address E2. One of the optimizations is that host 1, instead of using this MAC address and then forgetting about it, no, it will store the mapping IP2 and E2. This mapping is stored internally in an ARP cache memory, in a temporary memory that will store the MAC address and its corresponding IP address for some time. Why is this necessary? In case host 1 will a little bit later need to send another packet to host 2, it would have the mapping already. So let me go back here. Once a machine runs ARP, obviously by sending a broadcast request, it will cache the result. The result, which contains mapping, IP address, corresponding MAC address, will be cached in a temporary memory, in a cache memory, in case it will need it again after a little while. Okay, what else can be done? Imagine host 1 is sending this broadcast request. Host 1 is sending an ARP request. One of the nice things it can do is with the request itself, in which it is asking for this IP address, with the request itself, it includes its own mapping. So host 1 will be asking the following. You machines connected to my network, who owns this IP address? And by the way, my IP address, my own IP address is 192.32.65.7, and my MAC address is E1. So when the machines receive the request, they would know about the fact that there is a machine having this IP address and having this MAC address, so this can be stored. So in this example, when host 2 gets the request, it will have to reply with its own MAC address. However, it can store also the MAC address of host 1 in case it needs to be sending. So if a little bit later host 2 needs to send something to host 1, it has the mapping already. So we have this in the text as well. So host 1 will include its own IP to Ethernet mapping in its ARP request. So when the broadcast request arrives at host 2, it would know that there is someone having this IP address and having this MAC address. In case I need to reply a little bit later, I don't have to redo this ARP. So host number 2 in this case, if it needs to reply to host 1, it does not have to apply ARP. It does not have to send an ARP request. That's why we call it an optimization, since we are trying to save the network bandwidth. We are trying to avoid unnecessary ARP requests from being transmitted. Now, what else can be done? At the very beginning, once a machine gets connected to the network, just to begin with, even if it still does not need to send an actual data message, it will broadcast its own mapping. So once I get connected, I'm a host, I will get connected to a network. On my local network, I will broadcast my mapping. So I will send a broadcast message that contains my IP address and my MAC address, so that when people need to send me something, they have it in their own cache memory, and this avoids sending unnecessary ARP requests. Okay, since these mappings that have been stored, so host number 2, when it replied, it contained its own mapping here, which can be stored by people connected to the same network. Now, the final issue I wanted to say is that once I store an IP address and the MAC address mapping in my cache memory, it does not stay in my memory forever. So this is here. This is what we wanted to say here. It does not stay. So this mapping does not stay in my cache memory forever, just to allow these mappings to change. What happens if my IP address changes for a reason, or if I get disconnected from this network, I become part of the other network. So I have another IP address to MAC address mapping to allow for these things once I store a mapping in my cache memory to be used after a timeout period. So after a timeout period, that entry gets refreshed. So I remove this entry from my cache, which means if I need to send to this machine again, I have to run ARP. So this is the trade-off. So we try to avoid unnecessary requests. However, we have to refresh our cache memory to avoid any mistakes. Obviously, if that cache memory stays forever and that machine changes, it goes somewhere else or so, or it's, let's say its Ethernet card breaks, it will be changed. It has another MAC address, so my entry will not be correct and we will make mistakes. So this is the trade-off: avoiding unnecessary ARP requests and at the same time avoiding transmission mistakes. So that's why when I cache a mapping IP to MAC in my cache memory, it does not stay forever. It gets wiped out. It gets refreshed after a few minutes typically, and this is the timeout period involved. So this finishes this topic, ARP, and we have only one topic left, IP version 6, which we will cover in the next video, inshallah. Assalamu alaikum wa rahmatullah.